The most common gas component of natural gas hydrates, NGH, is methane, which appears to be primarily of biogenic origin. This has been confirmed in passive continental margins such as the Blake Ridge off the SE U.S., where deep thermogenic sources do not appear to have been tapped, and carbon isotope data indicates that biogenic methane dominates. Even in active margin areas, however, biogenic methane is much more common than thermogenic methane. Hello my friends, welcome to my Energy Economist channel. We will talk about gas production in this video. Stay with me. Biogenic gas directly feeding gas hydrate stability zone, GHSZ, has been observed in drill holes. Of the many drill holes into oceanic NGH, only a few have more than a few percent of thermogenic gas or traces of liquid hydrocarbons. Where deeper hydrocarbon sources are tapped by deep faults, thermogenic gas may be a locally prominent component of the gas mixture along with traces of liquid petroleum. Such deep faulting is common in accretionary margins such as Cascadia. Natural gas liquids, NGL, of higher carbon number gases such as ethane, propane, and butane that might be expected to form under GHSZ pressure and temperature conditions have not been observed in association with petroleum-related thermogenic NGH. The NGL will not be present so long as there is water for them to react with. These gases have a stronger preference for forming NGH than methane, and complete sequestration of them in compound NGH in the presence of water is the rule. NGH is rarely associated with liquid hydrocarbons, even when the gas has a thermogenic source, although in some rare cases, where a very active conventional petroleum system leaks to the seabed, NGH and liquid petroleum may occur together, as has been observed locally in the Gulf of Mexico. Passive margins without deep faulting that could tap a thermogenic deep petroleum system, such as exist on the basin/continental margins of both the Amur-Asia and Eurasia basins in the high Arctic, appear to be overwhelmingly sourced by biogenic methane. The NGH concentrations can be expected to be of high purity. This could be important to opening NGH exploration and production in the Arctic Ocean because the risk of pollution in the event of an accident that might release some gas is extremely low. Apart from gas that can be observed naturally venting from the sea floor, the presence of bottom simulating reflectors, BSRs, on seismic sections is first-order evidence for natural gas production and retention. But BSRs give little direct evidence about the potential for NGH concentrations. A BSR is useful only in the very early stages of exploration. The BSR is a reflection at a negative acoustic impedance contrast caused by free gas in the sediment below NGH in the GHSZ. Acoustic impedance is calculated as the product of compressional wave velocity times density. An acoustic reflection is produced at any interface where a contrast in acoustic impedance exists. The presence of gas below the BSR markedly lowers the velocity, and the gas NGH above increases the velocity somewhat compared to water-saturated sediments. A BSR does not mean that a gas column above water is present, especially in muddy sediments with low permeability where diffusion may be the primary mechanism of gas migration. Where an inclined permeable horizon crosses into a GHSZ, however, it is common to find gas pull below NGH in pore space. Estimates of leakage at the seafloor combined with gas and NGH in place will allow estimates of gas flux to be made. A first order of approximation for adequate gas flux, however, will be provided by the existence of the NGH itself. If gas flux were not high enough, no NGH would form. Even in the lower portion of the GHSZ, however, NGH concentrations with no BSR have been observed. This appears to have occurred when pore water solutions in the sediments immediately below NGH-enriched strata have been undersaturated with respect to gas generation so that no free gas is present. However, in the observed case, the saturation was apparently high enough to provide a driving force for NGH crystallization once the solutions reached the GHSZ. NGH concentrations can also form well above the base of the GHSZ from solutions that were relatively undersaturated and in which the driving force for NGH crystallization was too low until they have migrated to shallower depths where saturation increases as a function of lower pressure and where temperature is colder. These higher-level NGH concentrations will be indistinguishable from deposits formed from solutions formed lower in the GHSZ because the conditions governing crystallization will be the same. In lower-grade deposits that tend to be finer-grained, muddier, and less well-bed differentiated, continuous BSRs often occur at approximately the location of the base of the GHSZ and may extend over large areas. BSRs, whose importance has been overemphasized in the past, often constitute first-order features on seismic sections. These well-defined BSRs, such as are seen in the Blake Ridge area of the U.S. East Coast continental margin, are dramatic seismic features but are of limited exploration and economic value beyond identifying the region as a gas province. The NGH associated with these features often forms extremely large, low-grade deposits that have relatively small percentages of between 3% and 8% NGH in diffusely defined horizons throughout huge volumes of fairly uniform muddy sediments. These do not constitute primary exploration targets. The total amount of biogenic gas at a typical sedimentary site results from a cumulative process that potentially may have gone on over a long period of time. Methane is created by bacteria in sediments within and below the GHSZ, but at temperatures lower than the oil window. Where gas is formed below the GHSZ, it will tend to rise as bubbles and by diffusion. When it enters the GHSZ, it can react with water to form NGH. As sedimentation goes on, new sediment will bury older strata. Heat flow will tend to remain the same, so the thermal gradient beneath the seafloor will remain constant, as the GHSZ will maintain a nearly constant thickness during sedimentation. The result is that isotherms will rise to accommodate the accumulating strata because any given isotherm will maintain a constant sub-bottom depth below the surface. Pressure, which is dependent on water depth, will not change much, so the warming of deeper strata as isotherms rise to maintain the thermal structure of the GHSZ causes an upward migration of the base of the GHSZ. The upward migration of the base of the GHSZ through the sediments will result in dissociation of previously formed NGH that had been at the base of the GHSZ. The released gas will migrate upward, nourishing formation of new NGH in the subjacent GHSZ. This combined process of formation of new biogenic gas and recycling of basal GHSZ NGH will have the effect of increasing the amount of NGH in deposits and can go on as long as sedimentary accretion, including organic carbon, continues. Deep gas does not need to be sourced so long as the sediments/NGH accumulation system at depths less than the depth of the oil window functions appropriately. Methane occurs naturally due to the biological decomposition of organic matter available on the Earth's surface and is frequently manifested as marsh gas from wastelands, ponds, etc. Large gas reserves under the Earth have been detected where methane exists as crystals, gas hydrates, formed due to the interaction with water and methane molecules as a clathrate compound at high pressure and low temperature, usually below 20 degrees Celsius. Because of the abundance of methane gas formed in the geological period under the Earth's surface, usually in the Arctic region below the seabed, which is enough to saturate water at a very low temperature, methane hydrates are formed. Gas hydrates have been found at depths of 200 meters to 1,000 meters in the sea. Below this depth, ice layers, permafrost, permanent frost, of water is prevalent. The temperature of seawater decreases as depth increases, and the rate of decreases in temperature with respect to the depth is known as hydrothermal gradient. While the geothermal temperature below the seabed increases at a rate of 34 degrees Celsius per km. Thus, gas hydrates exist only a few hundred meters below the seabed where the temperature is below 20 degrees Celsius, and after this depth they cannot exist because of higher temperature due to geothermal conditions. Gas hydrates are lighter than water. Once dislodged from the bulk, it floats on the seawater and gradually releases methane from the sea surface. Hydrates are stable up to a maximum temperature of 15 degrees Celsius. Hence, if the temperature increases above 15 degrees Celsius, gas will be released from the hydrate. In fact, other hydrocarbon gases such as ethane, propane, butane, carbon dioxide, and helium may also be present in the hydrates along with methane. The presence of these gases also contributes to the stability of gas hydrates in a range of temperatures. Hydrate reserves are identified by the seismic exploration method. Approximately 164 nm3 of methane is available from 1 cubic meter of gas hydrate containing 0.2 cubic meter of gas and 0.8 cubic meter of water. Exploration is carried out during winter while the subsea level is favorable for stable gas hydrates in the reserve. If you want to learn more about gas production, you could do so in my book, Economics of Oil and Gas Production, which is published on Amazon. Check it out at the link in the description. Please take a second to hit the like button, hit the subscribe button, and do not forget to also hit the notification bell. Thank you for watching, and goodbye.